Hello everyone, we're Group 11 and today we're going to discuss and present to you about Thomas Kuhn's book, The Structure of Scientific Revolutions. But first, let us have a background overview about the book. The Structure of Scientific Revolutions by Thomas S. Kuhn is an important book in the history and philosophy of science. It changed how people think about scientific progress. Instead of seeing science as something that steadily builds up knowledge, Kuhn suggested that science moves forward in stages. Most of the time, scientists work within a shared set of ideas, or a paradigm. But every now and then, unexpected discoveries or anomalies challenge the current ideas. When this happens, a scientific evolution occurs, leading to a new set of ideas that changes how scientists understand and study the world. These new ideas don't just solve old problems. They also create new questions and guide future research in new directions. And today we're going to only focus on 4 chapters of the book. Chapter 4, Normal Science as Puzzle Solving. Chapter 5, The Priority of Paradigms. Chapter 6, Anomaly and the Emergence of Scientific Discoveries. And Chapter 10, Revolutions as Changes of Worldview. In Chapter 4, Normal Science as Puzzle Solving, Kuhn highlights that the essence of normal scientific work is solving puzzles rather than generating groundbreaking discoveries. This often aims to refining existing knowledge rather than discovering entirely new phenomena. Scientists discovering within a paradigm focus on addressing questions whose answers they expect to fit within that paradigm's framework. However, if the results deviate too far from the expected outcomes, the failure is often attributed to the scientist's error, not to the nature. An example Kuhn uses is Coulomb's experiments on electrical attraction, where results were largely anticipated because they aligned with existing paradigms. The results were unremarkable because they confirmed what was already predicted. However, failures to produce clear results, as with early attempts to measure electrical attraction, were overlooked because they did not fit within the established framework. Kuhn argues that the value of normal scientific problems lies in their ability to refine the precision and applicability of a paradigm, rather than in producing unexpected results. The fascination with problem solving in science derives from the challenge of finding new methods to achieve the expected, rather than from the excitement of discovering the unexpected. Scientists are driven by the intellectual challenge and the recognition of successfully navigating these problems. Kuhn compares normal science to solving puzzles like jigsaw puzzles or crossword puzzles. What makes a puzzle scientifically engaging is not the intrinsic value of its outcome, but the assurance that a solution exists and that it is attainable through the correct application of the paradigm's rules. Scientists then focus on problems where the solution is not only assured, but constrained by the established laws of the paradigm, limiting to what kind of results are acceptable. These rules within scientific paradigms govern both experimental and theoretical approaches, much like how the rules of a jigsaw puzzle dictate that all pieces must fit together in a specific way. These rules are derived from paradigms and include everything from how instruments are used to the kinds of solutions that are considered valid. Even more fundamental are the metaphysical assumptions underlying scientific paradigms. Kuhn uses the example of corpuscular theory, which dominated physical science from the 17th century onward, to illustrate how paradigms shape the types of questions scientists ask and the kinds of solutions they seek. At the core, normal science progresses within a rigid framework defined by the paradigm. Scientists' efforts focus on solving intricate puzzles defined by the framework. Yet, Kuhn points out that paradigms, not rules alone, guide research. A paradigm may continue to shape research even when explicit rules are absent. This puzzle-solving analogy reveals that highly structured, rule-bound nature of normal science, while also acknowledging that science inquiry is not entirely confined by rules. The paradigm, encompassing shared assumptions and viewpoints, ultimately drives scientific progress during periods of normal science.
In the next chapter, or Chapter 5, we will be explaining that shared paradigms don't necessarily mean shared rules. If we want to understand the consistency of a research tradition through rules, we need to identify some agreements or common ground. Scientists can agree that great minds like Newton or Einstein solved important problems, but they might not agree on why those solutions are effective. They can recognize a paradigm without fully understanding or explaining it. Even without a complete set of rules, a paradigm can still guide scientific research. Normal science relies on these paradigms even if the rules aren't fully defined. Kuhn reiterated Wittgenstein's idea that we don't need a strict set of rules to identify things like games, chairs, or leaves. Instead, we recognize them because they share a family resemblance to other things we've already learned to identify. This means that even without a clear definition, we can still understand and categorize new things based on their similarities to what we already know. This idea helps explain how a scientist can follow a paradigm and conduct normal science without needing a complete set of rules. Scientists often use models they learn during their education and from reading scientific literature without needing to know exactly why these models are considered important. They don't need a complete set of rules to follow these models. The consistency in their research doesn't necessarily mean there are hidden rules behind it. Scientists usually don't question what makes a problem or solution valid because it's not relevant to their work. Paradigms or accepted models guide their research more strongly and completely than any set of rules could. This means paradigms can shape normal science without needing explicit rules. This is because it's hard to pinpoint the exact rules that guide scientific traditions, similar to how it's hard to define what all leaves, chairs, and games have in common. Scientists learn concepts, laws, and theories through practical examples and applications, not just abstract definitions. New theories are accepted when they can be applied to real-world phenomena and are included in textbooks for future scientists to learn from. Kuhn used an example in the book in where a physicist and a chemist were asked if a helium atom is a molecule. The chemist said yes because it acts like one in gases, while the physicist said no because it doesn't show a molecular spectrum. Their different training led to different answers. This shows how paradigms can vary within a field and how these differences can influence what is considered revolutionary. In short, while paradigms guide scientific research, their specific applications and interpretations can differ among subgroups, meaning a revolution in one area might not affect others.
Now, let us talk about Chapter 6, Anomaly and the Emergence of Scientific Discoveries. In science, normal research follows a structured pattern, where scientists work within an established paradigm, solving puzzles and extending knowledge. However, groundbreaking discoveries often happen when these norms are challenged by anomalies, observations, or phenomena that don't fit within the scientific framework. Normal science is like a puzzle-solving activity. It is cumulative and successful in increasing precision and scope, but it doesn't aim for new facts or theories. These emerge unexpectedly, leading to paradigm shifts. A paradigm is like a set of rules under which normal science operates. When an anomaly is discovered, it indicates a flaw or gap in the existing paradigm, pushing scientists to reconsider their understanding of nature. A key process in scientific discovery begins with recognizing these anomalies. When scientists notice that their current understanding fails to explain certain observations, they enter a phase of exploration, which may lead to revising the paradigm. Let's take the discovery of oxygen as an example. Joseph Priestley in 1774 conducted experiments that led him to isolate a gas, which he initially misidentified. Meanwhile, Anton Lavoisier, building on Priestley's work, correctly identified this gas as oxygen. However, this discovery wasn't just about identifying a new substance. It led to the revolutionary oxygen theory of combustion, replacing the outdated phlogiston theory and transforming the field of chemistry. Scientific discoveries are rarely instant, single acts. They are complex processes involving conceptual shift that take time. Just as it took several years for oxygen to be fully understood, other discoveries follow similar paths, where new phenomena slowly emerge into scientific recognition. Let us now discuss the nature of discovery. The discovery of X-rays by Wilhelm Röntgen in 1895 also exemplifies this process. Initially, Röntgen noticed that the screen glowed unexpectedly during an experiment. This anomaly set him on a path of investigation that ultimately led to the discovery of X-rays, another phenomena that didn't fit within the scientific paradigms of the time. The discovery of such phenomena forces scientists to reconsider and sometimes drastically change their theories, methods, and instruments. This is what makes scientific discovery both challenging and transformative. In summary, scientific discoveries emerge from anomalies, unexpected results that challenge the current paradigm. These discoveries are not just about identifying something new, but about reshaping how scientists understand and interpret the natural world. Paradigm shifts are the driving force behind scientific progress, and recognizing anomalies is often the first step in this revolutionary process. So for the last chapter, chapter 10, Revolutions as Changes of Worldview. This chapter explores how scientific revolutions are not merely about new discoveries, but involve a fundamental change in how scientists perceive and understand the world. It argues that when paradigms shift, it is as though the world itself changes in the eyes of the scientists. This transformation is akin to a gestal switch, where scientists begin to see familiar things differently. Imagine you are looking at the same data with the same instruments, but suddenly, you see something completely new. That's what happens when a scientific revolution occurs. Scientists move to a new paradigm, and what they once thought they understood now looks different. The shift is so profound. It is like being transported to another world, where objects once familiar are now seen in a new light. Scientific training plays a key role in this transformation. Just as a student learns to see familiar patterns in complex data, like a physicist identifying subatomic particles in a bubble chamber, scientists undergoing a paradigm shift are re-educated. They learn to see what the old paradigm couldn't reveal. As scientists undergo training, their perception of the scientific world changes. What was once incomprehensible or anomalous becomes familiar through experience and exposure. Students of science undergo a transformation where they begin to see and interpret the world by seasoned scientists. Kuhn compares these shifts in science to gestal experiments, where our perception changes based on our experiences. For instance, wearing inverting lenses initially flips our visual world upside down, but with time, our brain adapts and we begin to see the world normally again. Similarly, in science, once a new paradigm is learned, scientists see things they couldn't before. Let us look at history for some concrete examples. In the 18th century, astronomers observed a star multiple times, not realizing it was Uranus. After Herschel's paradigm shift in astronomy, Uranus was recognized as a planet, changing the world of astronomy. Another example is Galileo's discovery of the pendulum, where Aristotelians saw constrained thought. Galileo saw periodic motion, a revelation that would shape modern physics. Now, it is important to understand that these changes aren't just new interpretations of old data. The data itself changes because the paradigm shapes what we observe. When scientists shift paradigms, they don't just reinterpret. They see the world in a whole completely different way. It is not simply adjusting their viewpoint. It is a whole new way of interacting with the scientific world. These paradigm shifts often happen during times of crisis in science. Normal science hits roadblocks, and the old paradigm can no longer explain the anomalies. Then, In a sudden moment of clarity, like a flash of intuition, the new paradigm emerges. It is like the scales falling from a scientist's eyes, allowing them to see and solve problems in a completely new way. In conclusion, scientific revolutions bring about a profound shift in how we perceive the world. The data we see, the tools we use, and the way we interpret the world all change. These transformations allow science to advance, not just by adding new facts, but by giving us new eyes with which to see the universe.
The second half of Chapter 10 talks about the continuous scientific revolutions of thought as new paradigms replace old ones, reshaping our understanding of the natural world. Thomas Kuhn argued that scientific observation is deeply influenced by the prevailing theories and paradigms of the time. He makes an example of the contrasting approaches of Aristotle and Galileo to the study of motion. Aristotle and Galileo approached motion differently, leading to contrasting conclusions about falling objects. Aristotle believed that objects fell to reach their natural resting position, focusing on total distance and time to develop the concept of average speed. Galileo, by studying factors like angular displacement and pendulum swings, identified motion patterns Aristotle missed, shaping their differing views on the laws of motion. Thomas Kuhn explores how scientific observations and experiments are influenced by the paradigms and theories that scientists operate within. He argues that sensory experiences or immediate experiences are not neutral or fixed but are shaped by current theories, making them unreliable as raw data. Instead, Kuhn suggests focusing on stable measurements and experiments performed in the lab to ensure consistency in scientific observations. He also touches on the challenge of creating a neutral observation language, as our perceptions are influenced by psychological factors and existing paradigms, making truly objective observations difficult to make. Kuhn also highlights the role of paradigms in determining the kinds of experiments scientists perform and the measurements they take. For example, the way scientists study pendulums differs from how they study falling objects, because each is influenced by different theoretical frameworks. Attempts to create a neutral observation language often fail because they rely on the very paradigms they aim to escape. This suggests that scientific observations are always somewhat theory-driven, and that creating an objective or neutral language for describing observations is a significant challenge. Kuhn further emphasizes how scientific training and culture shape what scientists see. When a trained scientist observes a swinging object, they see a pendulum, not just a falling object, because their background informs their perception. In this way, scientific understanding is not specific but holistic. Scientists grasp large areas of experience shaped by their paradigms. Only after being trained within a particular paradigm can they begin to ask precise questions and seek specific definitions. Even when scientific paradigms shift, many of the same experiments are continued to be used, although they may be interpreted differently in light of new theories. For instance, an experiment that once revealed one insight might produce new results when reconsidered through a different scientific framework. This shows how science evolves, not by discarding old knowledge, but by reinterpreting it through new paradigms that offer fresh perspectives on existing data. The development of chemical theories in the late 18th century offers a clear example of this. The theory of affinity, which explained how particles of elements attracted each other to form compounds, was challenged by John Dalton's atomic theory. While many chemists initially resisted Dalton's ideas, his new system, which emphasized the fixed proportion of elements in chemical reactions, eventually became widely accepted. Dalton's ideas not only clarified existing chemical data, but also led to new discoveries. demonstrating how a shift in scientific thinking can reshape an entire field.
And that's all. Thank you for listening and watching our presentation.